Continuing where we left off with representing displacement vectors by arrows. We marked positions with balls. We calculated the displacement that takes you from one position to another. So, for instance, line 15 calculates the displacement, takes you from red to green, so it's green minus red, new minus old, and that is represented by the arrow given the name VEC_RG. The position of the arrow is where the tail is. The actual content of the arrow that uses it, that represents the vector, is the actual displacement that takes you from the red to the green. So there are a couple other aspects of vectors that we can calculate. One is the size of the vector, or what we call the magnitude. How long is the arrow? So I'm going to go back up here to line 15 to put things in logical places. Actually, let's go down to line 19. Put cursor at the end, make a new line, and I want to print. Do a couple spaces so it's indented a little. So red to green, the vector representing that displacement, the vector that is that displacement, has the components 1, 7, 0. It's over here. So what is the size of that displacement? What is its magnitude? Now we could use the Pythagorean theorem, but script VPython will do the work for you. So inside the quotations, I will write with magnitude. Magnitude is a name for size. And outside the quotations, a comma. And I want to calculate the size of this arrow. I do not want to type in all the math of the Pythagorean theorem because VPython has a function that will do that called mag, for magnitude. So inside the parentheses, the vector whose magnitude I want to calculate, which is the displacement, disp_RG. So I can calculate the magnitude of a vector and print it out. Show you that that works. Magnitude 7.07. Does that sound about right? Well, 1 squared plus 7 squared. 7 squared is 49. So 1 plus 49 is 50. So it's a square root of 50. That looks about right. Another thing I might want to calculate is, suppose I don't want the whole displacement vector. I just want a unit vector. I just want a vector that points in that direction but has unit size. And then the components of that tell me something about the angles from x, y, z. So print, inside quotations, do a couple spaces to indent it. And let's call this with direction unit vector. Outside the quotations, comma, and this process of calculating a unit vector that points in the same direction, in other words, taking the vector and dividing by its magnitude, dividing by its size, is called norm, N-O-R-M. So N-O-R-M, disp_RG. So that is a vector. If you want, you can check that its magnitude is 1, square the 3 components, add them together, take the square root, it's 1. And each of these components can be related to an angle from an axis. Just for completeness, you can check that normalization calculation. Check norm. calc, go outside the parentheses, comma, we can take the displacement vector, rg, and divide it by its magnitude, mag, displacement, rg. And get the same number. It's just a little easier to use the norm function. Okay, remember to save often. Okay, so where was I? Okay, so let's put a couple blank lines in here to break things up. So we have do the same thing for green to blue, blue to red, so you can pause the video and take it out and then come back. Okay, so here's what I got for the new lines. Do green to blue. And blue to red. And okay, we want to be able to see everything. So I'll expand the output printing window. Does it look about right? Well, for red to green, it goes a little in the X and a lot in the Y. The green to blue goes a lot downward, negative in the Y, not in the X, not quite as much in the Y. And for the blue to red, goes in positive X, negative Y about equally. So that looks about right. One last check is we ended up where we started. We went from red, displacement yellow arrow to green, displacement cyan arrow to blue, displacement magenta arrow to red. So the total displacement, new line, total displacement, then a comma after the quotations. I should be able to add the three displacements. Displacement RG plus displacement GB plus displacement BR. That takes me from red to green to blue back to red again. Think for a second what the result of that should be. What is my total displacement here? From the very beginning to the very end. Looks like I made a mistake here. Yeah. So put displace plus GB. That's supposed to be an underscore. I made that mistake earlier, but you didn't notice because I did it when I wasn't recording. Total displacement 0, 0, 0. We ended up where we started. So that is what we would expect. Another way of looking at it is if we print where we ended, which is the position of red, minus where we started, which was the position of red, that will give us the total displacement again. And I'm not going to print any text with that. There we go. So arrows are a very good representation of vectors. Very physically, you can see how they take you from one place to another, how displacement is a good example of a vector. Velocity is also a vector, in which case you would simply divide by the time it took to go each of these displacements, each of these places to places. So change of position for time, that's the velocity. So these arrows could also represent the velocity vectors, the average velocity vectors. Very well.